Hi, this is Pete Singer with Semiconductor Digest, and I'm here talking to Joe Sestari, who is the general manager at Atonarp, and he is in charge of the mass spectrometry program there. And Joe, I think maybe a good place to start would just be to talk about the complexity of today's semiconductor manufacturing processes. Etch and CVD, there's so much going on inside the chamber. And why is it important for people to understand what's going on in real time inside the chamber?
Well, that's a simple question, yet a question that might take us another 2 hours to answer. No, I mean, if you look back, and for me, I've been in the industry now since the mid '80s, and it's amazing to think about what we're doing today. And really, if you think about everything in the sub 10 nanometer range, and you think about something like ALD or ALE, and literally by its name, atomic layer, right? And so we're dealing with atoms, not microns anymore. And the complexity of the number of layers in a process, the complexity of the geometric dimensions of a device, the chemistry, I mean, it's really not any one thing, but everything has become infinitely more complex. And on the other hand, even though we can look at the industry and the amazing growth, and certainly unprecedented right now, the pressure on pricing, because we are now a ubiquitous business that is, there's a semiconductor device in almost everything we touch every day. The ASP of the product compared to the days when we were only dealing with microprocessors and memory has drastically changed. So we have a very different and complex and almost every consumer driven demand market. And on the technology side, we continue to amaze ourselves, but on the other hand, we continue to look for ways to automate things, to get more intelligence, and to have better yield, more throughput. Right now, if everybody could increase their throughput by 20%, I'm sure it would have a fundamental impact to the overall supply chain challenges that everybody's dealing with. So it's a complex problem in and of itself in one technical area, and then it's a huge, complicated problem if you think about it from a holistic standpoint.
Mm-hmm. Okay, and so people have traditionally used techniques such as optical emission spectroscopy or RGAs, residual gas analyzers, to look into the chamber. But you have developed a new product based on mass spectrometry. And for me, I always think of some huge offline big system, but these are very compact units. I wondered if you could explain a little bit about how that unit works and what the new capabilities are.
Yeah, sure, I'd be happy to. I mean, at the basic scientific level, as you said, we are a mass spectrometry product. So from a physics and a science standpoint, it is still a mass spec product. What we've done, though, is looked at it both from the bottoms up and the tops down. And so from a technology standpoint, we've done a number of things, starting with our quadrupole sensor. We have found an effective way to machine hyperbolic rods instead of cylindrical rods, which are typically in a quadrupole. And that gives us greater sensitivity. It gives us greater response time. So at the root of the sensor you're using to measure molecular mass, that's important. Again, especially when we think of something at the atomic level, both from a sensitivity standpoint, but again, from a quantifiable resolution standpoint, that's critical. So our sensor is very different than what's out in the market. Again, there's quadrupole methods today used all over the place in mass spec, but we've taken a different approach to that device. So that's at the heart of the system. We've made that change. In terms of other things that we've done, we've looked at it for the last several years and realized there are a lot of great products out there in the RGA market and in optical emission spectroscopy and FTIR, a lot of great products. But to be effective, what you really need is something that can operate in situ real time if you're going to make decisions about your process. And when you have a 10-second or less process step, you can't afford to wait for a decision, right? And we've done and have still continue to do a lot of post-mortem metrology analysis, but unfortunately that doesn't change the yield of the particular product that you're making at the time. So several other things we've looked at is we have dual ionization sources in the product. So traditionally RGAs use a filament-based electron impact ionization source. And there's positive things in terms of performance about that technology, but no matter what kind of filament you use in a corrosive or deposition environment, it doesn't last too long. So again, as a diagnostic tool, it's great, but if you want something to use for process control and depend on that with the same reliability as your tool itself, that technology doesn't work. So we have also included in our product a plasma ionizer, essentially a mini chamber, just like you have on the tool, except much smaller. And what that allows us to do is, one, we have materials of construction of that wetted path that are corrosion resistant and can handle anything from a chemistry standpoint. The other thing we've built into the product is a novel feature that allows it to self-clean. So you can't avoid deposition in a plasma chamber. So we recognize that. And so while you're cleaning your process tool chamber with NF3 or CF4, we can use that same gas to clean the wetted path of our Aston product. So essentially we can operate in the same interval, same cadence as the tool does from a PM or cleaning standpoint, with no, we do use the electron impact for certain functions, but we're able to isolate it from a wetted path standpoint. So that question of reliability is gone. So those couple of performance features are really critical when you think about having a real-time process monitor. And as you mentioned, the other thing we've looked at, we all know how precious footprint is in a fab, certainly at the above the fab versus the sub fab. And we've tried to package the functionality all into one relatively small box. So we have a turbomolecular pump integrated, we have all the electronics integrated, the sensor integrated into one, again, compact platform. A lot of the other products out on the market today require you to kind of build it from an erector set standpoint into more of a cart version. So that physical footprint is important. And of course, the cost is important as well.
Sure. Yeah. There's so much going on within the chamber with reactants and byproducts and concentrations and partial pressures. I understand you look at all of those, you can measure those and monitor those in real time. Is that what can you give us an idea of the how that works in some key applications? I don't know, EUV or WF6 or anything like that.
Sure, be happy to. At the simplest level, it's obviously a combination of hardware and software. So as I mentioned before, we have a sensor that in terms of speed and sensitivity can give you that resolution that you need in a process. We're also focused on giving you quantified molecular level data. So we're not just giving you ratios, either peak ratios or ratios of a constituent in a full spectrum. We're actually quantifying each mass unit so that, again, you can make process decisions based upon that. So our software gives you the ability to look at not just partial pressures or ion current or things like that. You can actually get ppb level sensitivity based upon the molecular level presence, and whether that's a byproduct that's happening in the process chamber or whether that's a byproduct in the four-line when you're concerned about pump performance or pump integrity. That's a key thing. So yeah, a number of applications that we're involved in, and of course, as we all know, the sensitivity of the information is greater than ever. So we can't talk about specific customers or too many details, but we have been engaged in applications. We are doing some work on EUV source monitoring, both for a contamination monitoring standpoint, but also from a consistency of gases that might be used in that environment. So that is definitely one application that we're engaged with several customers. We have done a lot of applications on dry pump and abatement monitoring, both to understand the byproducts of the process, but also to be able to do proactive maintenance or diagnostics to save the life of a pump, and not have a catastrophic failure or even a perturbation that causes a yield issue. And then most of our work on the process side has been focused on ALD, a lot of interest in deposition, because today there isn't a product on the market that can operate in real time in the deposition environment. So tremendous amount of interest in looking at transitions between ALD cycles, but also in endpoint for ALD. And then we've had also a number of cases where OES, and you mentioned that earlier, is a very effective, very cost-effective solution for most, I'll say, commodity etch applications. But when you're talking about low open area or deep trench or very high stacked arrays, like in 3D NAND and things like that, we have shown that we're able to get to a very, very small percentage of open area in the sub 0.3% range, as compared to optical technology, which has a difficult time seeing down those large towers, typically more in the 3 to 5% range. So kind of a decade of, more than a decade of improvement in visibility, which is important for endpoint when you're looking at those etch applications.
Okay. And Joe, you'll be at Semicon West this year.
I will be personally, and we'll be there as a company as well. Looking forward to it. It's
okay. I will be too, so I hope to see you there. And I should mention in our latest issue, of October issue of Semiconductor Digest, there is an article on from Atonarp that goes into more detail on all of these things on page 30. So please check that out, dear audience.
I have read it. Thank you very much. It was a great honor and great coverage, and appreciate you taking the time to highlight us.
Okay. All right, Joe. Well, thank you very much.
Yeah, thanks, Pete. Appreciate it. Great to see you.
Good to see you.
Take care.